Section 3C is dealing with uncertainty, and this is in measurement and calculation and whatever else. So the first thing we talk about is random error versus systematic error. Um, Random errors occur because of inherently unpredictable events in the measurement process. Yep. And then systematic errors occur when there's a problem in the measurement system that affects all measurements in the same way. In other words, a systematic error is a consistent error. Device is off and it keeps giving the same incorrect error for the same reason, or incorrect reading for the same reason. So an example does a good job of illustrating the difference. So an instructor for a math class has graded the first exam. For question 1, you graded all students' exams with the wrong answer key. Which type of error is this? Well, all students' exams were graded with the wrong answer key. This is systematic. So in other words, what was consistent was the key was still used. So say the correct answer was 4 and the key said 5. Well, the students would have been systematically marked wrong in an incorrect way. So the mistake is made consistently by applying the key to every exam. And that's our consistent part of it. So it's a systematic error. Okay, so same situation. Now for question 2, the instructors continued. He's used the correct answer key this time, but he's unintentionally taken 3 points off for a certain incorrect answer for some students, but 2 points off for the same incorrect answer for other students. This is not an uncommon situation in grading, and it's not not on purpose, but it's just kind of accidentally happened. And in some cases, the same wrong answer of 3 is a student loses 3 points, and the same wrong answer of 3, another student might lose 2 points. There's no rhyme or reason to this. It's not consistent, and this is a random error. Okay, so that illustrates the difference between systematic error and a random error. The book has a few examples as well in this section or subsection. So absolute error and relative error. So here's a calculation that we'll do. The absolute error is the measured value minus the true value, if we happen to know the true or the actual value. Okay, so that's very similar to the absolute change, which is the new minus the old, or the new minus the reference. Okay, in fact, both of these are going to be similar to the change that we saw in section 3A. The relative error is the measured value minus the true value over the true value. Or in other words, new minus reference over reference, or new minus old over old. Okay, we're also converting this number to a percentage down here by multiplying by 100%. That's neither here nor there, but we'll just remember to convert a relative error to a percentage each time. Okay, so suppose you purchase 5 gallons of gasoline at the gas station, but the meter at this particular pump is uncalibrated and you only receive 4.5 gallons of gasoline. So the measured value in this case is 5 gallons. This is what the pump read, that's what you paid for. But the actual amount that you received was 4.5 gallons. Okay, so maybe you measured it into a container so you could check the meter on the pump. So the absolute error from this gas pump is the measured 5 gallons by the meter of the pump minus the 4.5 that you actually received, and that gives you 0.5 gallons. So the meter overestimated or had an error of 0.5 gallons. It was 0.5 gallons above what it actually gave you. Now for the relative error, we have the absolute error divided by the true value. So remember, this is actually the absolute error. So there's a nice shortcut in that, just like the relative error. So we already know the absolute error. That's 0.5 gallons divided by the true value. The true value again was 4.5 gallons. And I've added the units just as a callback to section 2 or chapter 2 to see that the units cancel, as they should if we're expecting to get a percentage as our answer. And 0.5 divided by 0.45 is 1/9 or 0.1 repeating. Rounding that to a decimal to the hundredths place is our percentage to the hundredths place is 11.11%. So the relative error is 11.11%. In other words, the meter on the pump has read that it gave you 11.11% more than what you actually got. So it overmeasured it or overestimated the measurement. Okay, accuracy and precision. So these are two similar concepts, but they are decidedly different. Accuracy describes how closely a measurement approximates a true value. In other words, a measurement that is more accurate has a smaller absolute error or smaller relative error as well. Okay, precision describes the amount of detail in a measurement. So one situation would be to measure in meters versus centimeters. Measuring in centimeters is more precise than measuring in meters. Measuring in inches is more precise than measuring in feet. Okay, so that's an idea of precision. So to see an example of it, there's another way we'll see precision show up. So it says, this example says, suppose you frequent two different gas stations and you suspect that their pumps are inaccurate. Why you do? I don't know, but you just do. I guess you're paranoid, you're a little bit OCD, so you decide to do something. You know that your car holds exactly 10 gallons of gasoline. Okay, so you run your car out of gas, possibly because you're a crazy person, right at this gas station, and then you're going to fill up. So when you fill up at the first gas station, it reads that you put 10.25 gallons into your car, but you know that it holds exactly 10 gallons. Okay, so it's off by a little bit, and you take note of that. Now you do the same thing at the second gas station, because you're absolutely crazy, and you run your car, which holds exactly 10 gallons, out of gas exactly the moment you get to this other gas station. You fill up, and the pump reads 10.29846 gallons after that. Okay, that's what the meter reads. In both cases, you know that you put in 10 gallons of gasoline. Which of these two is more accurate? This reading or this reading? Well, you can calculate the absolute error if you like and pick the one with the smaller absolute error. In the case that you get negative numbers, take the absolute value of the negative numbers just to see which one is closer to the actual measurement of 10. Well, just by inspecting these, we see that 10.25 is closer to 10 than 10.29846. So we know that Gas and Go is the more accurate of the two pumps. Okay? At the other gas station, Gasron, that one ends up being more precise because it's measuring out to 5 decimal places. That's to the nearest 100,000th of a gallon. That's extremely precise, okay? Whereas Gas and Go is measuring to the nearest 100th of a gallon. So both of those are probably just fine, but we note that Gasron measures to the nearest 100,000th of a gallon, or we just see that it has the longer decimal expansion in it, more decimals to it, so it's more precise thanks to that. So one of these was more accurate, the other one was more precise. Now, one thing to keep in mind when you look at these, or when you deal with these accuracy versus precision problems, oftentimes one measurement is more accurate, the other measurement is more precise. It's not necessarily the case that one has to be more accurate and one has to be more precise. You might have an exercise or an example in which one of the measurements is more accurate and also more precise, quite possibly. Okay, so just keep that in mind. They don't always have to split. Okay, significant digits. Significant digits is commonly, well understood by students in this class, but if it's new, slow down and pay attention to this section. If not, you can just, breeze through it, make sure everything is still what you expect. So there are 5 rules for significant digits. Non-zero digits are always significant. Okay, so anything that's not zero is always significant. Now, zeros that follow a non-zero digit and lie to the right of a decimal place. In other words, that 0 and these 2 zeros, these are always significant. Okay, those are telling us to what precision a measurement is made. So in other words, this number is not rounded from 4.19. It's been measured to be accurate to the nearest hundreds place. Okay, zeros between non-zero digits, here and here, or other significant digits. These two zeros are significant, so that makes this one significant as well, since these are always significant. Okay? Now, digits that are not significant. Zeros to the left of the first non-zero digit. These three zeros are not significant. These two zeros are not significant. They're just essentially placeholders. They're never significant. Zeros to the right of the last non-zero digit, but before the decimal point, are also not significant. They're just placeholders as well. They're to the right, but they're not to the right of a decimal point, so they're not giving us any amount of precision. This 42,000 number could have been rounded from 41,850, something like that, to be rounded to the nearest thousand. Okay, so those digits are not significant. Now, given a number, let's determine the number of significant digits in it. Well, we have 4 non-zero digits here, 1, 5, 3, and 7. So we have at least 4 significant digits, but rule number 5 tells us that this 0 is not significant, so we only have 4 significant digits. Next, 0.00349. Well, 3 non-zero digits is 3 significant figures so far, and any numbers to the left are handled by this, and they're never significant, so these are not significant. So we only have 3 significant digits for that number. Okay, one of the trickiest of all of these is 5.80 times 10 to the 6, this problem here. And we'll pause and just look at this. We're tempted to say there are 3 significant digits here. We ignore the scaling factor of 10 to the 6. That should always be the case. We'll always ignore the scale in scientific notation. In other words, the powers of 10 can be ignored for significant figures. And that's exactly true. This 0 is significant because of this rule up above, rule 2. Okay, it's a 0 to the right of the significant figures to the right of the decimal place. Okay, so that tells us to what degree, what accuracy this number has been measured. It's been measured out to 3 places here, so it's 3 significant digits. Were we to expand it so that we had 5,800,000, we would make a note with this number that is accurate to 3 significant digits, or it's precise to 3 significant digits. Okay, so that comment would accompany the expansion of this, but we don't need to make this expansion when we deal with these problems. We'll just leave it as is, and we can get the significant figures from this as well. In fact, significant digits were sort of built for scientific notation. They were kind of built with each other in mind. Now, the last one, 3.0049. Significant, significant. 3 significant digits. These zeros occur between significant digits. These are always significant. That's rule 3 up above. So we have 2 significant zeros plus 3 significant non-zero numbers, and we have 5 significant digits in this case. Okay, so there's more examples in the book for significant digits, so certainly check those out if this is new to you. Our last topic is combining measured numbers. So we have a rounding rule for addition or subtraction and a rounding rule for multiplication or division. When we round numbers that have been added or subtracted, we round our answer to the same precision or number of decimals as the least precise number in the calculation. Okay? When we multiply or divide, we round our answer to the same number of significant digits as the measurement with the fewest significant digits. So one is based on precision, the other one is based on significant digits. And we always use the least precise and the fewest significant digits to give us, the most fair representation of the precision or accuracy of our numbers. Okay, so a government of a local town has budgeted $52.25 million for the coming year. If there are 36,000 people in this town, what is the average amount of tax money the government will have to collect from each person? So this is to say that maybe everybody pays the same amount. All 36,000 people pay the same amount to make up $52.25 million. That's what this average person or average tax liability is. And what we do is we first form 52.25 million I've written that in scientific notation, times 10 to the 6 is 10 to the 6 is 1 million, so that's 52.25 million, reading the top, divided by the 36,000 people. A calculator tells us that this value is approximately equal to this number, with 8 repeating and rounding to a 9 pretty far out there. Now we go back in red and we look at significant figures. The top number has 4 significant figures. The bottom number has only 2 significant figures. We've multiplied or divided. In fact, we've divided. So we use the fewest number of significant figures in the entire problem, and that is actually this one. So our answer needs to have 2 significant figures. So we'll round this to 2 significant figures. In other words, we go to this 5 here, look to see whether, we go to this 4 here in the hundreds place, because we know we'll have a 1 in the thousands place, and we need to round this 4 either up or down based on whether or not that's 5 or greater. It's 5, so we round the 4 up to a 5 here. We end up with $1,500. We don't put cents right here, because if we were to put 0.00 at the end of this, that would give us 4 more significant figures, because these are significant, which would make these significant. We'd have 6 significant figures, and that would not match the 2 significant figures that we expected, or that we need to use for this answer. So what this tells us in this situation is that this is our rounded value, and it's based on the number of significant figures that we started with. This number was probably rounded anyway, which is why we round this number in the end here, to represent the fact that 36,000 was rounded as well. Okay, lastly, in a summary of monthly expenses, we find 3 amounts, and we add these up, these 3 amounts right here. We'll add them up as we have them, and we get a total of $938.50. What we note, though, is that this was carried to 50 cents to 2 decimal places. This one was carried to 2 decimal places. This was carried to 0 decimal places. So our precision is 2 decimal places, 2 decimal places, 0 decimal places. So $78 is the least precise value on this list. So we need to use this least precision to round this number, which means we need to round it to the nearest dollar, thanks to the 78 being rounded to the nearest dollar. So we round 938.5 to the nearest dollar, and we get 939. So $939, rounding that one as well. And that's again using the rule above. So that's it for section 3C. It's a little bit more of managing numbers and identifying significant figures, not as much calculation, but that should be a little bit easier compared to section 3A.